Today we have Jake Xuereb as the first speaker of the year. Jake, some people might recognize him from a podcast that has been done with him on thermodynamics and some press coverage that he's attracted in the past. So Jake is a researcher in quantum thermodynamics, originally from Malta. So he grew up and studied in Malta and then went on for a PhD in Vienna, which now is close to finishing, and he's been working on algorithms, thermodynamics, algorithms that harness thermodynamic ideas.
Yeah, let's get going. And sort of in spirit to Zoe and Iqui for also being happy to have me around. So yeah, today I'll be talking about this kind of recent publication we had in PRS Quantum called Cooling and Qubit Using and Others. But kind of, let's say, the puzzle I want to present you with is that, cooling ultimately can be seen as a game of permuting numbers around, and hopefully by the end of the talk you kind of get that, right? Cool. So, and this work was done with Ben Stratton, who's a finishing PhD student in Bristol, Jimmy Hay, who was a visiting undergrad student with us, Alberto Rolandi, a postdoc with us, my PhD supervisor, Marcus Huber, and the postdoc, Farnam Bashir. Cool. John already introduced me. I'm from Malta. This is Malta. I also organize these Calypso summer schools. Actually, Zoe taught at the first edition from which this photo was taken, so I assume she is somewhere in there. And this is a photo from the second summer school. They do not occur on boats. But we always have a boat trip around the island somewhere through the thing. And it seems like the boats get bigger progressively, so I really hope that this trend continues. We'll have the third one this summer, and the topics will be around Gibbs sampling, quantum optimization, and quantum thermodynamics. So if that sounds interesting to you, keep a lookout. And as John said, I'm part of Marcus Huber's group. Here you see us all sat in his pool, which is emptied in winter and uses as a board game space. And this is our coat of arms of the group. It has an interesting Latin phrase which you can't see, which is nunquam contingere laser theoricus, which just means don't let the theorists near the lasers, which I think is, makes sense. Okay, so what will I tell you about? I'll tell you about why people care about cooling, kind of from a theory perspective. Of course, there are many kind of experimental reasons why people care about cooling, of course. People trying to detect the quantum nature of gravity want to cool things down a lot so that they can create very good superpositions, but kind of as theorists, we also care about cooling for other reasons. I'll tell you about what it means to cool a system, and then we'll get into this problem that I will set up for you, and that somehow has this relationship with these kind of graphs and shuffling numbers around. Cool. I'll just set the timer. Cool. So cooling heralds new physics. I think throughout the history of physics, thermodynamics is somehow the operating system of physics, right? Any physical problem has energy in it. Thermodynamics is the theory of how we transfer energy in physical systems. So it's kind of no surprise that throughout history, first you had or in this kind of figure I have here, you have Sadi Carnot, who was this engineer in Napoleon's army and wanted to optimize steam engines, runs into the Carnot bound. You have Planck, who was studying the thermal radiation of black body objects, gives us quantum physics, and David Wineland and Doppler cooling, which ultimately now allows to do trapped ion quantum computation. So kind of somehow being at the limit of the thermodynamics of your current day seems to teach you something. Okay, so I think it's always a good thing to do. So what cooling do people care about in contemporary quantum thermodynamics? What's going on in that kind of area? And again, this is more my area, let's say the quantum information / quantum thermodynamics bent on this, because of course if you talk to a quantum optician, the way they think about cooling and kind of these people that cool down these resonator systems very cold and so on, they're going to think about this problem quite different from the way I will, so I will kind of try to give you these perspectives from my community. So there is this thing called autonomous Turing machines. You put some qubits together and you connect them to some large reservoirs at different temperatures, and you want some effect to happen. So in particular here, you have two qubits connected to like a cold reservoir and a hot reservoir, and you have a kind of like working medium qubit. And what ends up happening here is that you make the splitting of this qubit to be the difference between these two qubits. And when that happens, when heat is exchanged from hot to cold, you push this level up. And what this does is it allows you to build an engine out of this. And this was this kind of PRL from 2010 by Popescu and others. And in my opinion, it's a like clear answer to this challenge that Richard Feynman had set up like in the 50s. So if you've read one of his popular science books, like you will have read that he set this challenge of like, what's the smallest engine you can build? And then some people built this micromotor out of this pinhead and so on. But like now, you know, we've developed all these quantum information tools. We needed to also provide an answer for this. And I think this is a very compelling answer.
Just in this model that you're doing, is it important what kind of interaction happens three resonances?
I mean, it has to be tripartite. Actually, that's a nice question because we'll actually see the interaction in an example I will give. So I think you'll have an answer to that. So if I don't answer, we can come back to it. But I think you get it. So these are these autonomous Turing machines. They're autonomous in the sense that you just set up some bots, and then you just have an open quantum systems interaction, like a Lindbladian evolution. There's no agent driving it. There's no time-dependent Hamiltonian that some external agent needs to do. And this thing just happens. And then all the thermodynamics is self-contained, and you can study it. So this has been a big part of the field of quantum thermodynamics for the past 10, 15 years. So much so that people have started to build things out of these machines. So maybe in this diagram it doesn't make too much sense, but basically here again I have the 3-qubit engine, a cold qubit, a hot qubit, the working medium qubit, and now I add a ladder system. And again the ladder system will have this splitting, which is the difference of these two. And now you kind of just go up the ladder as this guy gets excited. And when you go to the top, then the probability of letting out a photon is very high. And maybe you want to use that photon as the tick of a clock. It turns out that the temperature difference between these two qubits directly influences the accuracy of this clock, so like the regularity at which you emit photons. And this became this like quite nice minimal model for how to build a quantum clock. Later on, people have talked about how to do computations with these guys. But yeah, so kind of cooling this problem of this engine led people to think also about like how to construct clocks, how to construct things that can do computations out of these guys. So this is kind of an important thing. And more recently, the 3-qubit fridge was used for an erasure protocol on superconducting qubits in Simone Gasparinetti's lab. And so this type of community is kind of suggesting, look, like maybe the insights from quantum thermodynamics can even help us do some very basic subroutines in quantum computation. You know, is this the case? These people seem to think so. Another style of quantum thermodynamic problem in this vein is the so-called algorithmic cooling problem from the 90s by Vazirani. And this is basically a generalization of the fridge problem, where you have one qubit that you want to cool, and then you have n identical copies of this qubit, and you're going to push entropy out of your system qubit into the other guys. So you could imagine that in this erasure protocol, having more qubits is better for you. But these things, these kind of two lines of research I've showed you, are a bit limited in two distinct ways. So if we take the fridge, okay, there is some intricacy in the fridge, the gaps vary, interesting things happen, but they're quite small. On the other hand, the algorithmic cooling problem, you have like identical qubits, and complicated interactions, and it can be quite big. So you have these two issues. So in our problem, we just said, okay, let's do both, right? Like, let's cool one qubit, but let's let this machine, the secondary system that we're going to use to cool this guy, have any gap we want. And then let's just study the cooling problem in full generality. So this is the thing I'm going to talk to you about for the next 20 minutes, half hours, this problem. But before we get into that, what does it mean to cool a quantum system anyway, right? Like, really and truly, if we want to think about this problem. So, the cooling, of course, is lowering the temperature. But what is the temperature of a quantum system? Well, temperature as a Lagrange multiplier is kind of a phrase you could attack this question with. And what that means is just that temperature is nothing more than a property of probability distributions that have a certain form. So if we take a two-level system, you're going to have some ground and excited states given to you by this Hamiltonian, and you could collect statistics of how many times I see excitations and not. You build your histogram, and then you could ask, well, does my histogram respect this distribution for this Hamiltonian? And if that's the case, then we can call it the thermal distribution. And in this sense, this guy is showing up as this Lagrange multiplier. Okay, so now we understand the math. What does it mean to cool then? How do you make beta? Larger, right? The inverse temperature larger. So you fix the energy omega in this Hamiltonian. You'll increase beta. So increasing the ground state population, purifying the system directly cools the system. Cool. Of course, this logic stands if you make the system larger, like a qubit, whatever you want. For simplicity of the problem, I'm going to talk to you about the two-level system. If you're still fascinated by that, by larger systems, ask me about it at the end of the talk, and I can tell you some kind of insights there. But so then, our general problem is the following. I have some quantum system I want to cool. I'm going to give you access to a secondary quantum system. That's going to be our auxiliary quantum system, our so-called machine, where I want to dump entropy into it and kind of steal purity from it. And I'm going to do a unitary on these two together, and I want to see, yeah, how much can I increase the ground state population of this qubit? And in particular, when is this a hard thing to do and why? The structure of this unitary, when is it complicated? When does it need to touch many qubits in this setting, right? So these are the type of things I want to care about. Why? So in Marcus's group, a big theme of research in the past 5 years has been kind of showing why cooling quantum systems is hard. So famously, probably everyone knows the third law of thermodynamics, this Nernst theorem, that if you want to take a quantum system and cool it or even a classical system and cool it to 0 temperature, you're going to run into an infinity somewhere, like the dimension of the thing you're using to cool, or the amount of time it takes to cool the system. But it wasn't clear for quantum systems how this thing would play out. And in this paper called Landauer versus Nernst, which is a play on the fact that there is this Landauer bound, which lower bounds the heat you dissipate when you delete a bit of information. In this paper, they study this exact thing of like, why is it hard? And they kind of identify a couple different ways in which this could become hard, which namely the unitary you're going to use to cool might become very complex in the sense of circuit complexity. Your time, in this sense of like how many gates you need, might also become very big. So you might imagine that if you had like 2 body operators, you might need a very deep circuit, whereas if you had like an n-partite operator, maybe you just need 1. The structural complexity of the machine, which means like the variety of energy gaps in your Hamiltonian, if you have a very large variety, cooling is easier. Or the energy of this guy. If it's an infinite energy thing, you have a pure state, trade your pure state in, you've cooled to 0. So these are the kind of different ways in which cooling can be hard. And this is a nice paper, but when I joined the group and I read this paper, I was a bit disappointed because it's in full generality. They don't really show how you can trade these things off against each other. So my motivation in considering this n-qubit problem is to explore how to trade these things off one another, and that's hopefully what we will see. Okay, so exactly, this is going to be the problem we're going to tackle. We have our system of interest, with some gap omega at temperature Ts. I'm going to give you n other qubits at temperature Tm, and they all have different gaps, gamma 1 through gamma n, and I want to use that to cool this system qubit. So in the same spirit that here I want to see how these things trade each other off, the structural complexity is going to be given by these gammas of these machine qubits. The control complexity we're going to be able to see in the unitary. How complicated is this unitary? How, is it k-partite, n-partite? How many things is it touching? And then indeed these will be the two main things we're going to kind of interest ourselves in this problem. Okay, so before we treat the general problem, maybe let's take a 3-qubit example. I always like examples. So we have 3 qubits. It's going to be an 8 by 8 density matrix. All these 2-level guys are diagonal because they're thermal states in the same basis. Indeed, for the sake of this problem, I'm going to take these to be separable thermal states. It doesn't really matter, but it makes the kind of explainability of the thing a bit nicer. But yeah, so we're going to have this scenario. And we recall that we want to make the ground state population of the first guy larger. Okay, so we have our system qubit and our machine qubits. I'll make the system qubit correspond to the first index, and the machine qubits correspond to the second two. And what that means is basically that the sum of these 4 numbers, the sum of these 4 populations, corresponds to the ground state population of the system, whereas the sum of these guys is the excited state population. Okay, and we have unitaries, right? And all these 8 numbers are eigenvalues. And unitaries preserve eigenvalues, so I can't really change these numbers. So it's not like I can make one number grow and that's going to help me. But what I can do is find numbers from this block of the density matrix that correspond to the excited subspace of the system. And if they are larger than numbers up here, I can trade them from here to here, such that I increase the sum. Okay, so this is going to be the type of game we're going to want to play. And in particular, in this 3-qubit problem, what one finds is that this number down here is by construction always larger than this number, and sometimes this number might also be larger than this number. Why? Okay, and we will call these like disordered populations, in the sense that if I put this number up here, now, and this number up here, now all the big numbers are at the top, and they're ordered. They're disordered in the sense that if I order these 4 numbers, I will have cooled S. So they're disordered relative to my class. Okay, why does this happen? Oh, and to answer John's question earlier, in the 3-qubit fridge, it is exactly this exchange which happens between the 2 qubits that form the bath qubits, the bath contacts, and your system qubit. So the fridge, the fridge or the 3-qubit engine, the way it works is that you kind of have your strokes in the engine that cause these populations to oscillate up and down, and that's how you kind of construct the fridge. Okay, but why is it the case that this is always bigger than this? Well, it's the case because by design, I've set that I want this guy to be hotter than these two, or maybe just as hot. Ideally, these are colder, right? I want to use them for cooling. And I also want omega to be less than or equal to gamma and gamma 2. And why? Again, these are my resourceful guys, so I want them to be larger than omega. That being said, even if they're all equal, this will still hold, because I have 2 energies on the right-hand side. So because by construction I always have this interaction will always cool, trading this energy level in the 3-qubit Hilbert space for this energy level. Okay, what about the orange guy? Well, the orange guy happens if this condition holds. And let's think about what this condition tells us. It tells us that the energy of the system qubit need be smaller than the difference between these 2 machine qubits, which you can imagine is not always true, right? It depends. But interestingly, if this were true, because it's a difference of these two and this is a sum, then this implies this. Okay, there's kind of an energetic hierarchy in these two scenarios. That's what I just said, that there's this energetic hierarchy here. But this gives two distinct cases, and I've just introduced this kind of graphic notation for this problem, and because it will prove to be useful. And so case A is the case where I have this one difference between these numbers, these single pair of disordered populations. Case B is where I have two of them. Okay, now the reason why they're called Boolean hypercubes, okay? So you take your bit strings that are indexing your Hilbert space and you form a connection between them if they vary by one bit. Why is this nice? This is nice because it allows you to really visualize what unitaries do here easily. In what sense? So maybe notice the following thing. If I do a sigma x on the third qubit, okay, the third bit, it flips from a 0 to a 1, it's like I have a plane which is cutting through the cube here, and I just flip the cube. Similarly, if I want to do a sigma x on the second qubit, it's like a plane going through the cube horizontally, and I flip it, okay? A swap is a flip of the cube through a diagonal plane, and when I start doing controlled operations, if I want to have my sigma x on qubit 3, and I condition it on the first qubit being in a 0, then I'll only get the flip on this front face. Okay, so this is kind of nice to try to think through this. And notice the following. Single qubit operations flip the whole cube, 2 qubit operations flip a face, and the 3 qubit operation, such as the Toffoli, right, which would take us from 110 to 111, if I flip this one with this one, that's a Toffoli, so a 3 qubit interaction acts only on an edge. Okay. And here, interestingly, right, if there are 1, 2, 3 Toffolis that take me from that guy to that guy. So if I had 3 qubit operations, I could do this. Whereas this one is different because here I have 2 pairs, but this opens me up to the fact that because I'm going to exchange pairs, I can just use a 2 qubit operation, which ends up being the full swap here. Okay, let's maybe also see this in the population. So if you go through the math of exchanging this one and this one, the change in population is this number. Okay, so I gained this population, I lost this population, weighted by the partition function. And I also had my initial population. And you can see that this number is larger than this number. Whereas in case B, after you do the math of these 2 exchanges, the number you get out is simply the population of qubit 2, machine qubit 2. So it must be that it's a bipartite operation. Right, so these are 2 different cases which are dictated by the energetic structure of the machine, right? This is what I want to impress upon you, is that in both cases, this guy is the same. The only thing that changes is how the energies of these 2 are distributed. How the energies of these 2 are distributed is changing the unitary I need to quote-unquote optimally cool the qubit. Why? Because in either case, I leave nothing on the table. If there's disorder, I want to make it go away. Of course, I could just do this, but then in the bipartite case, I would have left this disorder, so I could have cooled further. So the requirement for optimal cooling is dependent on the energetic structure of the machine, and this influences the structure of the unitary I require. Since these cubes are fun and I like them, I can also show you a visual proof of why you can't do the tripartite scenario with bipartite operations, okay? Because you might say like, well, Jake, okay, you showed us this change in population argument, but like, you have not conclusively shown me that you couldn't, I don't know, there is no set of single phase operations that exchange this one and this one, right? You could say that. Okay, but let's try and do it, right? So, for example, what would we want to do, right? We want to bring this red ball, and these are the disordered populations, I'm just drawing them. I want to bring them on the same edge, and then flip through a face, right? That's kind of what I would want to do. Okay, so we can do this. We'll do 2 qubit operations, or allowed control X operations. We flip this face. This guy comes here. But now let's keep track of this wall, which we just exchanged from here. Okay? Now I'm going to flip through this face. This wall comes up with me. And again, this wall is ordered so far, right? All the ground state population guys are on this side, all the excited state populations are on this side. So this guy so far is one of the ordered guys. I don't need to flip it around. But now when I come to trade across this face, because I can't trade through an edge, I must trade through a face, I will bring this blue guy along with me when I exchange these red guys, causing a new error. Okay? So this is kind of an argument to show you that the tripartite, in the tripartite scenario, where you just have one pair to trade, a tripartite operation is necessary. Of course, I'm making one assumption here, which is that because we start with a fully diagonal state, I'm only considering operations that permute elements on the diagonal. I'm not considering stuff that can create coherences. Because thermodynamically, if I create the coherences, I have to make them go away at the end. Because I know I have to return to a diagonal. So I'm only considering permutations of the eigenbasis, which means in this case, operations generated by sigma x are enough. Okay, so all that to say, a C0 or a swap is not enough to give you one of these guys. And if you know stuff about circuit compilation, that also means a C0 or a swap in any conjunction will never give you a toffoli, for example, right? Because here I need a toffoli to trade through an edge. If you look at the paper and the appendix, I also give a bit more like group representation argument for why it's the case, but maybe that's only for the people that are nerdy enough to care about these things. Okay, nice. So we've done an example, and we've basically learned why the energetic structure of the machine leads to different cases, right? Let's now see this in the general problem. So in the general problem, we want to attack 3 points. Point 1, where are the disordered populations in this vector of the system and the machine? Which are the populations that I need to trade to cool? Is there any structure? Clearly it's dependent on the energy of the machine, but can we understand it more? Secondly, is the machine reducible? Okay, what do I mean by reducible? When we had the 3 qubit case where it ended up being bipartite, and I just interacted with 1 qubit from the machine, that means the middle qubit was a waste. It didn't even need to be there in the machine because I just traded with the colder guy. Another way to think about this is, if I do the tripartite interaction, I'm using the 2 qubits in the machine together to create some kind of like effective qubit that's even colder than those 2 separately, right? Like there's some sort of subspace, some single qubit subspace in that 2 qubit Hilbert space, which is colder than any of them individually. But in the case where we had this bipartite case, it won't be true that this effective qubit is colder than any of them individually. Which is to say, I could have thrown one of them. Away in the bipartite case. Does this ever happen? Can we predict this? Because if we're thermodynamicists that want to design these engines, these multi-qubit engines, well, when I tell an experimentalist to build it, I should make sure that they don't put any extra qubits there that they're not using, right? I want to make sure that in the cooling interaction I tell them to build, that cooling interaction is going to use all the qubits that you constructed. So, let's try to keep track of this. And then we will ask which unitary should we use to cool relative to some cost function. Maybe how much energy we dissipate into the machine, and maybe the circuit complexity. We want to kind of look at this. Okay, so point 1, where are the disordered pairs? Okay, mathematically this is kind of very simple to see. Why? I'm going to introduce a bit string notation because we're working with n qubits, right? So I'll have an n bit string from I1 to In, and I'll consider a dot product with this vector of energies of the machine, gamma 1 through gamma n. And this dot product will just like enumerate all the energies of the machine. Okay, so you can imagine that if you had your 0, 1, 1, right, that this has energy gamma 1 plus gamma 2. And all I'm saying is that if you have like some I1, I2 dot gamma 1, gamma 2, that if this were the case, 1, 1 dot gamma 1, gamma 2, then I will get this gamma 1 plus gamma 2. Okay, so that's what this notation is allowing me to do. Nice. And then we care about this inequality. What is this inequality? Any ground state population looks like this, divided by the partition function. Any excited state population looks like this, divided by the partition function. What's the difference? Here we have the 1, an excitation from the system. Here we don't have an excitation from the system. And again, we want to find a number from the ground state populations that's smaller than a number from the excited state populations, because when we trade them, we will cool the system. Nice. You can kind of go through the math, and you'll find this interesting inequality. So here you have the temperature of the machine, and the temperature of the system, the ratio, the energy of the machine, and if the change in energy you cause when doing your permutation of these energy levels is larger than this ratio of the temperatures, you should do it. It's going to cool. So this set of inequalities, which you would need to check in principle for both I and J, tells you if you cool or not. Okay? Now, this might be a bit scary that we need to check I and J, but we're going to find a way to simplify this dramatically. Yeah, for any computer science people in the room, this is also a bit related to the knapsack problem, in the sense that I want to find a set of numbers, right, which are smaller than some number. So I have my bag of populations, and now I find out that there's some like property, and I need to find which subset of them satisfy this property. So yeah.
Just to get back. So here you say you cool when omega delta Ts is smaller than whatever.
Then the change you will call it. Yeah.
And this is independent of what kind of interaction you use. It's just purely.
So far, exactly, we're just checking which numbers on this vector we need to exchange. Now, what exchange we need to use is kind of part 2, and this is, we'll kind of get to this. I don't know if that, like in the sense that, in this example, we're just finding out which of these are smaller than these. Then how do you trade these two? There's like there's two ways of doing that here, right? If you have two numbers. So that kind of gets to the interaction then, right? Because after we've identified our disordered populations, then we need to discuss how do we exchange them. Okay, so now, we found this inequality, it detects disorder. It looks a bit scary. Can we simplify it? The answer is yes, because we can realize that there's a bit of like an order going on here. So these are the energy levels of the machine, indexed by bit strings, and this is the energies they correspond to. And basically, you can realize that there's some symmetry here, because if I take the bit string with 2 1s, it's gamma 1 plus gamma 2 away from the smallest energy. And if I look at the bit string with 2 zeros, the Hamming weight conjugate, it's gamma 1 plus gamma 2 away from the maximum energy. Why is this nice? This means that if I start checking these inequalities and using these Hamming weight differences, so I say, is this one, is trading this one with this one good for me? That's like the largest delta E available at the time, right? Because I'm always checking this delta E. Now, if the largest delta E is not good, then there will be no delta E smaller than it, which will also beat it, right? So when you start checking from the biggest in this hierarchy, if it fails at any point, you can stop checking. And the nice thing is that because then I can index all the bit strings from one side and the other using the same IM, and I use this Hamming weight conjugacy, it also kind of simplifies the inequality to this final form. So there is an energy 0s IM in the ground state subspace, which I should exchange for an energy 1s IM O plus 1, this Hamming weight conjugate in the excited state subspace, if this energy E of IM is larger than the ratio plus the maximum energy in the machine divided by 1/2. you can think of this as, it tells you where the effective median is in this like set of numbers. Okay, but this is nice because instead of having to optimize over I and j, you can just optimize over one of them and you find all of them. Okay, so that was kind of a bit of a technical insight in the paper. One final thing about this, it also reveals a bit of like a Carnot efficiency bound on how much energy you can change in a single computation, which is unexpected because you should not be able to find a Carnot bound here because you do not have a thermal state of your machine at the end of the process. But all this to say that the Carnot efficiency, right, is 1 minus the ratio of your temperature differences, and you will never be able to change the energy of your system by some difference delta E normalized by the energy of the machine, or sorry, of the system, more than the Carnot efficiency. So this is a bit like of a nice quirk you get on. Okay, point 2. These interactions, how do I know if I need a k-partite interaction or a n-partite interaction with the machine? Well, basically, we can ask the question, when is it that a qubit pops out of my unitary, that I don't need to use it? I don't need to use it if its corresponding index in the unitary is a free index. Now these are all bits. What does it mean? It means that I have some fixed bit string, and it's like there's one bit, right? Imagine here, okay? What are we saying here? We're saying I'm using, there's a 1 here, so I'm using the nth excitation of the machine, okay? But if I'm using the nth excitation of the machine, I need to trade it. But I also need to trade every other possibility of the other n minus 1 energies. Then they become free indices in this unitary, right? So again, I'll just say this again. I need to trade this 1. I need to trade this excitation. If when I'm trading this excitation in some set of energies indexed in this way, I notice that these guys in the unitary are free indices, then I can just do the unitary on 0 and 1 alone, right? They pop out. Maybe very, very quick. Very quick. So when we were trading earlier, right, we were seeing there's the 0, 1, 1 with 1, 0, 0. I always need to trade. And then in the 3-qubit example, and then there was the 0, 0, 0, 1, which I needed to trade sometimes, okay? If I needed to do both of them together, what do we notice here? It's that I'm always trading these. But the middle guy has now become a free index in that unitary. So the second qubit no longer plays a role in the unitary. There's an identity there. So it pops out. That's what I mean by free index. And the worst case is if you have an n qubit machine and n minus 1 of them don't contribute, which means I only use the final energy. This happens, okay, when all of all of these guys are disordered. So I need all of them larger than this quantity. In particular, even for the all 0 guy. And that means that when I have a machine where the largest qubit in the machine, the qubit with the largest gap in the machine, has a gap which is larger than basically half the sum of all of them. Okay, I'll say it again. The largest gap in the machine is larger than half the sum of all of them, then basically everything else pops out of the unitary. You just need to interact with the last one. Another way to think of this is that this last qubit is so cold that using all the others doesn't give you more. It's already that cold, this guy. And this is a condition for finding this. So this is like the worst case. When you're building a machine to cool a qubit, you would never want to do this. This is like the most dramatic thing that can happen because you need to throw away n minus 1 of them. And what about an irreducible machine, like the best kind of machine? You use all of it always. Well, what that means is that I need to use the weakest energy, okay? Using the weakest energy means I need to have my 1 in there for a fixed L, and I need to not have the 0 there. So it's not a free index, okay? And what does it mean to, I need this guy in there, and I need this guy not to be in there. Okay, so you get these two conditions. Together, you have the following. If there is at least one set of energies on the n-1 weakest qubits, so excluding the coldest guy, which satisfies this, then the machine is irreducible. Okay? There's a lot of math to say that the degenerate case, the case where you have n identical spins cooling one spin, like in algorithmic cooling, we gave the first proof that it's irreducible. So this is nice. It means that kind of this thing that many people have studied for over a decade is irreducible. You actually use all of them. Cool, and it's a nice proof, but we're running out of time. Reducibility in general, because now I showed you an irreducible condition. I showed you the n-1 reducible, where you throw out n of them. Now you could ask, Jake, what is the k reducible condition, right? Where you throw away k of them. That's very complicated, because you have this partial order, where here you see like, okay, if this energy is disordered, this energy must also be disordered. It becomes a free index, and then you stop there. But what if you're like here, and this guy is cooling? Then everything behind it must cool. And anyway, it's a whole mess. There's an appendix about it. Not so important. Final point before we close. We've identified k populations in the ground state subspace that are too small. We've identified k of them that are too big. How do we trade them? Here there are k factorial different unitaries. So there's many to choose from. We need a way to choose them, because they can vary wildly, right? They could be very simple unitaries with low circuit depth. They could be unitaries that are very complicated. They could throw a lot of heat into the machine, or they could not. We need to optimize. But nicely, we can translate this into a computer science problem, namely finding minimum weight perfect matchings. So a matching is just like you take a set of vertices, you have some edges which connect them, and then you need to and you find a set of edges that connect some vertices. That's a matching. A perfect matching is when the number of vertices you're trying to connect is the same, and the minimum weight perfect matching is when you have a cost function on top of that. Now, for us, here's what like if I have a 3-qubit machine and 1 qubit I'm trying to cool, what these kind of graphs look like. And notice that like the set of things I need to trade is different in each guy, and that the number of them is different in each guy, and that there could be many different unitaries of doing this. So you would write down all of these. So these are all eigenkets, right? And basically any unitary that trades these 3 eigenkets here, for example, for these 3 eigenkets is a valid cooling unitary that will cool optimally for me. But which eigenket I'm pairing with which, I need to find a way to choose that. And the way of doing that is by writing down such a graph with the eigenkets you want to swap on the ground state on one side, the eigenkets you want to swap from the excited state, the subspace on the other side. You write down your cost function of interest. It might be the Hamming weight, which kind of lower bounds the circuit complexity. It might be the energy change they cause, which is the dissipation. And there are algorithms for optimizing this, and we look into this in the paper. Okay, so what I'm trying to convince you of here is that there are many such unitaries. Like here, for example, there would be 3 factorial, there would be 4 factorial there. And for different cost functions, there's going to be different optimal choices of unitaries. And this is equivalent to a minimum weight perfect matching problem for which you can optimize. Okay, so to summarize, the energetic structure of the machine dictates how much you can cool and how you can cool it. That this is all explained in the n-qubit kind of cooling problem with general gaps by a hierarchy of inequalities that are hierarchical in the energy. When designing a cooling machine, we should make sure that it's not reducible, so that we make sure our experimental strands are not being wasteful. And if we want to optimize unitaries that cool our system, we can do so by relating it to a minimum weight perfect matching problem. So that's what I have to say to you today. Thanks very much for your attention.